Assalamu alaikum students. Today's topic is going to be about Doppler effect. Let us read about it. The apparent change in frequency is the motion of either the source of sound or the listener or both is called Doppler effect. That means the frequency, the wavelength may change when the source, the listener or both are moving. The Doppler effect interrelates the measured frequency of wave relative to the velocity of source of sound and receiver. That means that whenever there is a change in velocity of either the receiver who is listening to that sound or the source, the sound will change. This phenomena is called Doppler effect. After Christian Jonathan Doppler, who showed in 1842 that frequency shift should be observed for sound light waves due to the relative motion between the source and observer. He showed that sound and light both can change when the source or the receiver are both moving. To further describe the Doppler effect, consider a source S emitting sound of wave velocity v, frequency f, and wavelength lambda. When the source S and the listener A are at rest, then the listener will receive frequency number of wave in 1 second like this. Now, if this car is representing the source and this person is the audience, or you can say A, then you can see the sound wave by by you can say the longitudinal wave. So it has compression and rarefaction. The sound will reach the other person and he will hear a frequency f, and the wavelength of that sound will be lambda. Now if we change the situation, the distance between the source and the listener is v. That means the point from here till here is v. Since f number of waves are compressed, the distance v, so the wavelength lambda is given by the simple formula lambda is equal to v over f, and f will be equal to v divided by lambda. So this is the formula for speed of sound, and we can just rearrange it to get the value of lambda as well as frequency. But what if they both were moving? Now in that case, if the source is moving towards the stationary listener, now what will happen in that case? Let the source of sound, or you can say source S, moving with the speed a towards the stationary listener L, shown in figure. Now here's the figure, that this is the source, this is now the listener L, and this car is moving with the velocity a. The first wave emitted by the source distance v after 1 second reaches the listener L. Now let us understand this with the help of animation. Now as it moves, the wave of sound basically is emitted by the car in the form of horn, and as it gets closer, as you can see, the wavelength is being compressed. It becomes smaller. Now as the wavelength is smaller, you can see the frequency becomes enlarged. So at the end of 1 second, the source covers the distance a when or where it gives the last wave. Thus in this case, f number of waves are compressed in distance b minus a. That means now the waves are only compressed in this region rather than this region, as shown in figure. So the apparent wavelength lambda dash is given by the change in velocity v minus a, which is the where v is the velocity of sound and a is the velocity of that vehicle, divided by the frequency. We get the change frequency, which is given by the same formula. F dash is equal to v divided by lambda dash. Now we know what is the lambda dash. Putting value of lambda dash in this equation, we get f dash is equal to v divided by v minus a. F goes up, so the change in frequency is given as f dash v over v minus a into f. Now if we look at the denominator and the numerator, which one is bigger? Of course, the numerator. Now something has to be multiplied by this f, that means the original frequency, so that it becomes equal to the change frequency. That means it was smaller, that is why something was being multiplied, so it becomes bigger. This equation shows that if the sounding source approaching the stationary listener, the frequency of sound or sound wave increases. Now, as the result, pitch of the sound also increases. So this person will hear a very large sound of the horn. Now, if we consider the same case but in opposite case, let's say the source is moving away from the stationary listener. Now, in this case, we have the same person who's L and the source is same and he's basically listening to the horn of the car. So what happens now? If the source, sound source S is moving away from the stationary listener, then F number of waves are contained in the distance V plus A. That means it has to be increased. The pavement wavelength lambda dash is given by V plus A divided by F. That means as the car is moving like this, so you can see the lambda is being increased. Now in this case, if the lambda is being increased, then what happens? The frequency decreases and this person will hear a smaller sound. Now let us solve it with the help of mathematics. The apparent frequency f dash is given by f dash is equal to v over v plus a. Where does the v over v plus a comes from? From lambda dash. So it was actually f dash is equal to v over lambda dash. When we put in the value of lambda, we get v over v plus a into f. Now, if we look at this denominator and numerator, we see that the denominator is bigger, so something small, very small has to be multiplied with this f to make it equal to f dash. That means we have to make it less this f so that it becomes equal to the f dash, the change frequency. So that proves that f dash, the new frequency, is now smaller than f, so the pitch of sound decreases when the sound source is moving away from the stationary listener. That means this person will hear a sound very less as the car is moving away from him. Now, another case. Now, instead of source, we are saying the listener moves towards the stationary sound source. Now, in this case, it is also possible when the listener moves towards the or away from the stationary source, the pitch of the sound changes. The listener moves towards the sound. Now, we'll discuss in this case. Let L be the listener moving towards with speed B towards the stationary sounding source as shown in figure. Now, here is a person listener and here's the source. Now this person will move towards the source with some velocity. Now what happens? What he will hear? Let's see. As you can see, the sound is moving towards the source, oh, sorry, the listener, and the listener is moving towards the source. Now, in this case, the listener basically is moving towards the source. In this case, we add speed of the listener with the speed of sound. We shall get the case in which the sound waves are moving with the speed v plus b, where v is the velocity of this sound and b is the velocity of this person moving towards the source of the sound, where source of the sound is at rest, so the speed of sound relative to the listener is b plus b and the wavelength remains the same. Now as you can see, there is no change in wavelength, neither it is compressed nor it is being you can say expand in this case. So in this case, the velocity we are adding up and decreasing. Therefore, the apparent frequency is now f double dash is equal to v plus b divided by lambda. Now this is the change in frequency. Now, as we know that lambda is same, so lambda is equal to v over f. If we basically put the value of lambda, this lambda, in this equation, we will get f double dash is equal to v plus b divided by v into f. Now, if we compare these two, numerator and denominator, we will see that numerator is larger than the denominator. That means f, the original frequency was less. That is why something has to be multiplied to it to make it equal to the change frequency. So f double dash is greater, so the pitch of sound increases when the listener moves towards the stationary source sounding object. Now, another case we have, if the listener moves away from the stationary source sounding. Now, in this case, it is also possible when the listener moves towards or away from the stationary source or the pitch of the sound. Now, in this case, the listener is moving away from the stationary source. Let L be the listener moving with the speed B, not towards but away. Now, in this case, we are considering away stationary source as shown in figure. Here we are, as we are moving away from the source. Now, what will the listener hear? In this case, we add the speed of the listener of speed of sound and get this case in the speed of wave moving with the speed of v minus b. That means now it is moving in the same direction, but as you know, the sound wave is not changing. Where the sound of the source of sound is at rest, so the speed of sound relative to the listener becomes v minus b. That means it has decreased in this case. So wavelength remain the same. As we know, the frequency has changed because of velocity. So we subtract the velocity of the person, which is b, from the velocity of the speed of sound, which is v divided by lambda. Now in this case, f double dash is equal to v minus b divided by lambda. Here lambda we already know it is equal to v over f. Putting value in this equation, therefore we get f double dash will be equal to v minus b divided by v into f. As you can see over here, the numerator is smaller, so that it multiplies with f. So f was bigger than f dash, so something small has to be multiplied to it, so that they become equal. So in this case, the person will hear a very small sound as he is moving away from the source. So f double dash will be smaller, so the pitch of the sound decreases when the listener moves away from the stationary source. Now another case, if source and listener both move towards each other, what will happen then? It is also possible when source and listener both move, the pitch of the sound changes. The source and listener both move towards each other. Now if, let's say this is the source and this is a listener, L, and they both are moving towards each other, what he will hear? Let's see. Just basically car makes a sound, and because it is moving towards the listener, the sound is being, basically the wavelength is being compressed actually over here. So this person will hear a very large sound because they both are moving towards each other. Now how can we explain this in the form of equation? If the source and listener are approaching each other with the velocity a and b, that means the velocity of the source was a and the velocity of the listener was b, then what happens respectively? Then the apparent wavelength lambda is given by lambda dash is equal to v minus a divided by f, and the velocity change because the observer or the listener was moving towards the source. The speed of sound relative to the listener will be v dash, which will be v plus b, because they were moving towards each other. Now in this case, the apparent frequency f dash will be f dash is equal to v dash divided by lambda dash. So if we solve it, what is v dash? It is v plus b. And what is lambda dash? It is v minus b, and f goes up, it will be over here. Now as we can see, the numerator is very much bigger as compared to the denominator. So from here we can calculate that this frequency was very small, so that a very large quantity has to be multiplied to it, so that it becomes equal to the change frequency. That means he will hear a very large sound. So here we have f dash will be equal to v plus b divided by v minus a into f, and here we have that f dash is very large than f, so the pitch of sound increases when the source and listener are approaching towards each other. Now, if the source and listener are moving away from each other, this is the last scenario. Now, if the source is moving away with the velocity a and the listener is moving away with the velocity b, now what happens? Now what he will hear? Now, in this case, as you can see, the lambda has increased massively. Now, in this case, let's see what happens. When the source of sound and listener move away from each other, the apparent wavelength lambda dash is given by lambda dash v plus a divided by f. And the speed of the relative to the listener will be v dash, which will be equal to v minus b. That means the velocity of this person and the speed of sound, v, will basically are moving, although in the same direction, but are lesser of amount because they are moving in the same direction. The apparent frequency is now given by, we know that f dash is equal to v dash divided by lambda dash. If we put in the values, we get v dash, we'll put v minus b, and instead of lambda dash, we'll put va plus f, which goes up right over here. So now we can write it down as f. So here we can see the numerator is smaller as compared to the denominator. So something smaller has to be multiplied with this f to make it equal to f dash. So here we can see f dash, the change in frequency is very, very small. So the pitch of sound decreases when the source and the listener move away from each other. So these were the 7 scenarios actually you can see in Doppler effect. I hope you enjoyed today's lecture. I certainly did. Inshallah, we'll meet again. Allah Hafiz.